Thank you for introduction. Today I will speak about Cryogels with incorporated gold and palladium nanoparticles and its application for catalysis. I will start with some results of bioremediation. I will speak about concept of cryogel preparation of ionic cryogels, and covalently cross-linked cryogels with in situ synthesized noble metal nanoparticles and their characterization. And also I will show the catalytic activity of obtained catalytic structure. It is known that triclosan and similar compounds such as triclocarbon has antimicrobial activity and found a wide application in toothpaste, soaps, detergents, and for surgical cleaning treatment. And the current bioremediation systems doesn't allow complete removal and degradation of this persistent compound. And therefore, every year, approximately 200 tons activated sludge after the treatment goes to the environment, to the fields. And of course, it leads to contamination of environment. So what we did, we tested the remediation of this chlor derivatives such as chlorophenols, dehalogenation, and we found that toxic compounds such as cresol and phenol, it can be removed using normal bioremediation, just in wastewater. It can be removed within 3 days. However, if we introduce some amount of chloride derivative chlorophenols, then it inhibits degradation of phenols and cresols. So it's toxic to most of bacteria, and therefore we need to find catalytic treatment in order to decrease concentration of these chlorophenols, to decrease toxicity, and then we can go with remediation, bioremediation. And this HPLC chromatogram shows that after 1 week, we still have phenol and chlorophenol. It didn't evaporate, it stayed, or it wasn't degraded. So how we prepare cryogels? If we mix a polymer with some cross-linking agent, and then we start to freeze the system, growing ice crystals expel solids into non-frozen liquid microphase, and this allows the reaction to proceed within liquid microphase. And after the melting of the system at room temperature, ice crystal melts and remains porous sponge-like material. We mixed hydrogen with tetrachloroauric acid, and they led to formation of some complex which was liquid at room temperature, but when we freeze it at moderate freezing, -12 centigrade degree, at least for 4 hours, then it leads to formation of ionic cryogel. And in order to check that this was due to ionic interactions, we added sodium chloride, which inhibits the ionic interaction, and therefore the formation of cold complex and the ionic cryogel was not formed, was not observed. And also when we used hydrochloric acid, low pH, then most of amino groups were in protonated state, and we didn't observe the formation of gel, and this gives us, we assume that we have not only ionic interactions but also ligand exchange, and therefore this gel is due to ionic interaction and ligand exchange. So if we incubate the reaction mixture of hydrazine with tetrachloroauric acid at 60 centigrade degree, it leads to formation of gold nanoparticle suspension. And if we do the same but with a hydrazine which was dissolved in hydrofluoric acid, then it leads to formation of only gold nanoplates. Ionic Cryogel also can be converted to gold nanoparticle suspension, not only due to incubation at a high temperature, but also due to UV irradiation or visible light irradiation, and then we observe this evolution of the hydrogel and slow formation of gold nanoparticles, and ultimately to dissolution of ionic cryogel to gold nanoparticle suspension. Over time, we did some modeling using Medusa software, and as one can see, in presence of ammonia, there can be ligand exchange with a hydroxyl group at pH around 3 and 4, and we assume that we have also possibility of ligand exchange with the primary amino groups of hydrazine. And also in literature we found some information regarding complex formation between gold and amino acids such as cysteine and aspartic acid, and therefore we assume that we have also formation of not only ionic interactions between oppositely charged groups, but also chelation process. Also, we found that we can form similar complexes with palladium and platinum. We did not observe formation of gel. We are mixing of platinum complex, platinum in hexachloride, and this is due to pH effect. So pH of the reaction mixture was low, and that led to protonation of all amino groups of hydrazine, and there were only electrostatic interactions, and electrostatic interactions are very fast. But at moderate pH, when hydrazine dissolved in acetic acid, we have formation of hydrogel, and when we freeze it, we get a porous structure hydrogel. And as one can see, this gel can be swollen, and the difference with the gold complex that these hydrogels and cryogels are stable to irradiation of light, but if it's necessary, we can recycle these gels by addition of EDTA, and that lead to dissolution of the hydrogel. One can see on the figure 7, this diagram shows the possibility of ligand exchange process. We did a simulation for the presence of ammonium cations, and we see that at pH around 5 we have formation of this complex, and therefore most probably the same happens with the hydrogen solution. Oppositely, if we compare the simulation for platinum complexes, we don't observe the possibility of ligand exchange for ammonia, and we have only formation of electrostatic interactions. So, and this also confirms that for formation of gels, we need to use only 0.4 millimole in case with palladium complex, and we need approximately 10 times more of platinum complex for formation of the gel with the hydrogen. So this difference is due to, in case with platinum, we have only electrostatic interaction, and then in case with palladium, we have electrostatic interactions and also halation process, ligand exchange process. And this correlates well with radiology data, and as one can see, we have a cross section between G prime and G double prime at approximately 3-4 minutes, which corresponds to transformation of the Zol to gel state, and that was observed for concentration 0.4 millimole of palladium and hydrogen solution. If we increase concentration of palladium, then gelation happens too fast, and it cannot be observed using radiology. So when we start to measure it, it's already a gel. And when we decrease concentration of palladium to 0.1 or to 0.2 millimole, then we don't observe the transformation of Zol to gel within like several hours. However, if we freeze this system, then for several hours, as I said, the freezing and thawing leads to formation of the gel, and usually when you freeze the system, the concentration of solids in non-frozen liquid microphase increases approximately 6-7 times, and then this triggers the formation of the gel. And when we run this Cryogel, it shows that this is the gel. The radiology data shows that now we have a gel. So obtained ionic cryogels can be converted to gold nanoparticle suspension using strong reducing agent such as sodium borohydrate. But if we want to stabilize the system and have three-dimensional polymeric network with incorporated gold or other noble metals particles inside of the structure, then we can cross-link the system using glutaral or other cross-linking agent, which will cross-link the polymer, and also it acts as a reducing agent due to difference in redox potential. For example, the redox potential for acetaldehyde and for glutaral is similar, and this metal complexes has high standard redox potential, and therefore they act as an oxidizing agent. So this is spontaneous reaction of a reduction process, and as a result, we have formation of nanoparticles, stable, mechanically stable porous system, and this data correlates with elemental mapping, which indicates that we have a well distribution of gold nanoparticles within the structure, and also it shows that with increase of concentration of gold complex, we have increased concentration of gold nanoparticles in the system. On these histograms, one can observe gold nanoparticles stabilized by Hyperzone, but the difference was only in the treatment. For instance, in this case, ionic Cryogel was incubated at 60 centigrade degree, and we got the average diameter of 2.8 plus minus 1.8 nanometers. If we dissolved ionic Cryogels where heat treatment, then it led to increase of average size to 7.4 nanometers. If we use just a reaction mixture of gold complex with a Hyperzone and straightforward heat treatment, then it leads to formation of gold nanoparticles with larger size and larger polydispersity index. And this is due to poor conversion of gold complex, incomplete ligand exchange. So the cryo treatment helps accelerates the ligand exchange, and therefore then we can get better, smaller gold nanoparticles or other nanoparticles. And also, as one can see here, when we reduce ionic Cryogel with a concentration of 1 millimole using glutaraldehyde, it leads to formation of gold nanoparticles with a size of 9 nanometers. In order to check its catalytic activity, we did the oxidation of dimethylamine benzaldehyde by dissolved oxygen, and it showed the catalytic activity in oxidation process. And then we did the experiment with a different concentration of gold nanoparticles in the system for reduction of nitrophenol. And as one can see, we observe the same angle after a number of cycles of reduction, which indicates about stability of the catalytic system and also high performance. And this is the schematic setup, experimental setup. So we run the spectra of the reaction mixture in a flow state every 1 minute. Palladium immobilized scaffolds showed also quite narrow distribution of nanoparticles, characterized by small size, and this system also was checked for reduction of nitrophenol, and it showed absence of inhibition of the catalytic activity over time. Then we would like to apply this catalytic system with a proven catalytic activity for a reduction process on dehalogenation of chlorophenols. And according to literature data, chlorophenols can be converted to phenols and then reduced to cyclohexanol, And what we observed using UV spectroscopy, that after 20 minutes, we have a conversion degree of about 26.6%, and that did not change after 24 hours. That can be related to some kind of inhibition of the catalytic process. And in this process, we didn't use sodium borehydride. We applied green reducing agent such as formic acid, which can be decomposed to carbon monoxide and hydrogen, and therefore this reaction is related to green chemistry. Again, we tried to apply gas chromatography for monitoring of concentration of products, and we observed that we have a decline, we have an incomplete conversion of chlorophenols. In order to optimize conditions, we assumed that probably we have a poisoning of palladium with chloride ions, and we introduced silver ions that can combine with the chloride ions and precipitate with the formation of silver chloride. However, this approach didn't help significantly to accelerate the reduction process or lead to complete reduction of the chlorophenols. And we didn't make this reaction at high temperature, as silver can oxidize phenolic group, silver in a zero valence state. Therefore, also what we did, we checked the catalytic activity of the catalyst in presence of sodium borehydride, and in this case also we didn't observe the complete conversion of chlorophenols, and probably the geometry of these particles are not suitable for significant adsorption of substrate to the surface, or the release of the product of a reaction is the limiting stage of this process. So when we increase temperature up to 80 centigrade, we observed a significant increase of conversion of the reaction. However, it was not completed. So this is HPLC data. Also, we tested dichlorophenol, and we observed the main peak of dichlorophenol and numerous peaks of side products of dehalogenation process. What we observed is that the optimal conditions was pH 3 and temperature approximately 80 centigrade, and the platinum was less active compared to palladium. HPLC data and also the control experiment on the image E that indicates that we don't have a leakage of any compounds from the scaffold, and all these observed peaks are related to derivatives of chlorophenols during the catalytic reaction. And this is the conclusion, that we managed to make cryogels flow through reactors for different catalytic reactions, and also we checked the catalytic reaction for dehalogenation process, which needs more detailed detailed investigation in future. Thank you for your attention, and acknowledgement to my advisory team and also to funding agencies. Thank you for your attention.